Okay everyone, let's tackle this question from matrices. It says that let A be a matrix which is not equal to identity matrix or negative of identity matrix. It's a 2 cross 2 real matrix, that means a 2 cross 2 matrix with real entries, such that A square is I being the unit matrix. Let TR of A represent trace of A be the sum of diagonal elements, the main diagonal. The sum of the entries sitting in the main diagonal of A, then trace of A is 0 and determinant of A is -1. These are two statements representing two different very claims, so I have to actually verify both the claims. I am given A square is equal to identity. Now what can I say after this? This means A into A is I. So there are two things that I can say. First thing is A into A is I. That means what? That means inverse of A is A only. A is self-inverse. If A square is identity, means A is self-inverse. That means A is same as A inverse. This is the first thing. Secondly, what I can say is if A square is I, then determinant of A square is same as determinant of I. Determinant of identity matrix you know is 1. So you have got determinant of A square is 1. But determinant of A square is same as determinant of A whole square, which is 1. Right? And if determinant of A whole square is 1, that means determinant of A is plus or minus 1. Okay, so two things we can infer from this single given expression that A square is I. One is that A is self-inverse, second is that determinant of A is plus or minus 1. Now please look at the second claim, it says that determinant of A is -1. If statement 2 has to be correct, then somehow I have to rule out the possibility of determinant of A being equal to +1. And if I get determinant of A equal to +1, then this statement would turn out to be false. So let's see, we're going to proceed step by step. I will have to assume A to be some 2 cross 2 real matrix. Suppose this is what it is. Now, A inverse is equal to A. By the way, what is A inverse? It is 1 upon determinant of A into transpose of all the cofactors of A, that is the adjoint of A matrix. Adjoint of A upon determinant of A is your A inverse. What comes out to be adjoint of A if A is a 2 cross 2 matrix? Directly you know, these two entries change the places and these two change their signs. This is my A inverse. If this is my A inverse is given to be equal to A. Now, case 1. If determinant of A is equal to 1. If determinant of A is equal to 1, what do you get over here? 1. So you will get, this implies 1 upon 1 is 1, D minus B minus CA is equal to A, B, C, D. Which would mean D is equal to A, minus B is equal to B, minus B is equal to B, or B plus B is 0, or 2B is 0, or B is 0. Minus C is equal to C, or 2C is 0, or C is 0. And A is equal to D, which I have already written. This is what you get. And what is determinant of A? Well, determinant of A is equal to 1 means if this is A, what is determinant of A? AD minus BC. Right, B and C are coming out to be 0. So you just get AD is equal to 1, but A is same as D. So you get A into A, that is A square is 1, which implies A is plus minus 1. So in this case, what are you getting as A? Matrix A is 1, B is 0, C is 0, D is equal to A. Either this or your A will be -1, 0, 0, -1, right? A has two possibilities, plus or minus 1. Whatever A will be, D will be the same as A, and B and C are 0. So capital A has two possibilities. But in this case, I want to say it is identity matrix of order 2 cross 2, and here I am going to say it is minus of identity matrix of order 2 cross 2. Both the things are not possible because it is given to me that A is a matrix other than I or minus I. So A cannot be equal to I, A cannot be equal to minus I. That means determinant of A is not equal to 1. Determinant of A is equal to -1. So this statement is actually true. Okay? Now if it is fixed that determinant of A is -1, that means what? If determinant of A we have confirmed that it is -1, now I have to verify about this statement that trace of A is 0. Trace of A means what? Over here if I talk about trace of A, sum of the main diagonal entries, these are my main diagonal entries. Sum of the main diagonal entries means A plus D. This I have to show to be equal to 0, okay, if that statement is true. Now determinant of A is fixed to be -1. If determinant of A is fixed to be -1, this is already true because this is holding. Why? Because this is holding. So if this determinant of A is -1, this means -1 times D minus B minus CA is equal to A, B, C, D. So from here you get minus D, minus of minus B is B, minus of minus C is C, minus A. This is equal to A, B, C, D. Okay. This means what? Minus D is equals to A firstly, or A plus D is 0, or trace of A is 0. So you are getting that yes, determinant of A is -1, and because determinant of A is -1, that is why trace of A is 0. So both the statements individually are correct, but statement 2 is correct reason for statement 1 to be correct. So statement 2 is being true because of which statement 1 is standing to be true. Okay, so they are not two independent statements whose truth value doesn't depend upon each other. They are true, but statement 1 is true when statement 2 has already been true. So statement 2 is the correct reason for statement 1 to be true. Okay? Let's take a look at the next question. What does it say? It says that A is a 3 cross 3 non-singular matrix. Now why is it given that A is non-singular? A is given to be non-singular so that there is a guarantee of the existence of A inverse, because you can see in the expression we are talking about A inverse. So that is guaranteed, okay, if I say A is non-singular, such that AA transpose is A transpose A and B is A inverse A transpose, and what is BB transpose? Carefully, B transpose. What is B? A inverse A transpose. A inverse A transpose. This is B. Then you have B transpose, that means A inverse A transpose transpose. Now you know A into B whole transpose is B transpose A transpose. So this is A inverse A transpose. This becomes A transpose transpose A inverse transpose. A transpose transpose into A inverse transpose, because A into B whole transpose is B transpose A transpose, reversal law of transpose. So this becomes A inverse A transpose. A transpose transpose is A, you know that, and this is A inverse transpose. Now I can write this as A transpose A inverse transpose. What is A transpose A? It is given as A transpose A is A transpose. So this will be A inverse A transpose A inverse transpose. A transpose is here. Now I can do what? A inverse A and A transpose A inverse transpose. What is A inverse A? A inverse A is identity matrix, right? Identity matrix of order 3 cross 3. And what is A transpose A inverse transpose? That means I am talking about A inverse into A whole transpose, isn't it? If I talk about A inverse into A whole transpose, that would mean A transpose into A inverse transpose. That's what I have, A transpose into A inverse transpose. So AB whole transpose is B transpose A transpose. So B transpose A transpose, B transpose A transpose can be written as A into B whole transpose. But A inverse into A is what? Again identity matrix of order 3 cross 3. And transpose of identity matrix of order 3 cross 3 is identity matrix of order 3 cross 3. So this is I into I, which is I square, which is again I. So BB transpose is coming out to be equal to I. Is it clear? So here we've used everything, the concepts of inverse, the concepts of transpose, reversal law of transpose, right, and the properties of identity matrix. So that has led us to the correct solution. Is it clear? Let's move to the next one. It says if B is a 3 cross 3 matrix such that B square is a null matrix of order 3. Okay, B square is a null matrix of order 3. Then I need to talk about determinant of I plus B whole to the power 50 minus 50 times B. So if you focus upon this thing first of all, if B square is a null matrix of order 3 cross 3, then B cube is also a null matrix of order 3 cross 3, B to the power 4 is also null matrix of order 3 cross 3, and so on. B to the power R is null matrix of order 3 cross 3 for all R greater than or equal to 2. If 2 is the first power for which B raised to some power is null, then any power beyond it, when B is raised to any power beyond that power, that is also null. Is it clear? Now it is asking us to compute the determinant of this matrix. If I talk about I plus B whole to the power 50, just open it up by using your binomial theorem. It is 50C0. It is 50C0, I to the power 50 minus 0, B to the power 0, which is nothing, identity only, plus 50C1, I to the power 50 minus 1, B to the power 1, plus 50C2, I to the power 50 minus 2, B to the power 2, plus and so on, 50C50, I to the power 50 minus 50, which is I to the power 0, which we are not writing, B to the power 50. Okay. Now see, 50C0 is 1, 1 into I to the power 50 is I to the power 50, but identity matrix raised to any power is that matrix only. So you are left with just I. After that, here you have 50C1 is 50, I to the power 49 is I only, I into B is B, so 50B, plus 50C2, I to the power 48 is I only, but B square is null matrix. Null matrix into anything is null matrix, right? And any scalar times null matrix is null matrix. So this is null matrix of order 3 cross 3. After that you will have B cube coming up, which is again null matrix. B to the power 4, again null matrix, and so on till B to the power 50, again null matrix. So you will have all these are null matrices of order 3 cross 3. So when you add any finitely many number of null matrices with each other, the answer is a null matrix only. So this complete thing is going to come out to be null matrix of order 3 cross 3, and because this is additive identity, so this when I add with any matrix, I get back that matrix. So this matrix added with null matrix gives me this matrix. Okay? So you have this is equal to this. So how can I write this? I plus B whole to the power 50 minus 50B is equal to I, and that is the matrix I have to calculate the determinant of. I have to calculate the determinant of I plus B to the power 50 minus 50B, that is this determinant. So determinant of this is equal to determinant of this. Determinant of identity matrix is 1, and that gives me the determinant of this matrix, which is 1. Is it clear? That's how you evaluate this question, okay? Next question says that if A is 5A minus B 3, 2, it is a 2 cross 2 matrix given to you, and A into adjoint of A is AA transpose, then 5A plus B will be equal to what? Just try to recollect your knowledge on this. If you can recall, what was A into adjoint of A? A into adjoint of A was determinant of A times identity matrix of the order same as that of A. Here it is 2 cross 2. Remember this very important result. A into adjoint of A is determinant of A times identity matrix of the same order as that of A. In fact, we had done it like this. If A is a square matrix of order n, then A into adjoint of A is determinant of A times I n cross n, right? So here the same result is being valid for 2 cross 2, n equals 2 basically. This thing is also given equal to AA transpose. So A into adjoint of A already is equal to this, and I am given that A into adjoint of A is equal to AA transpose. So A into adjoint of A is equal to this also, and it is equal to this also. That means these two are equal for this given matrix, right? So you are having AA transpose is equal to determinant of A times identity matrix of order 2 cross 2. What is A? A is 5A minus B 3 2. This is my A. A transpose will be 5A minus B 3 2. So first row becomes first column, second row becomes second column. This is equal to determinant of A. What is determinant of A? Product of diagonal minus product of off diagonal. 5A into 2 is 10A minus B into 3, which is plus 3B. So 10A plus 3B times identity matrix of order 2 cross 2, which is 1 0 0 1. Cool enough? Let us multiply. What do you get? 25A square plus B square. This into this, and then you have this into this. So 15A minus 2B, right? 15A minus 2B. Then you have this into this, 15A minus 2B again. And here you have 9 plus 4, which is 13. Okay, so first row into first column gave me what? 25A square plus B square. Then first row into second column gave me 15A minus 2B. Then second row into first column I got 15A minus 2B again. And then second row into second column 9 plus 4, that is 13. This is coming out to be equal to 10A plus 3B into 1, which is 10A plus 3B. 10A plus 3B into 0 is 0. Here also 0, and here 10A plus 3B. Okay. So if two matrices of the same order are actually equal to each other, that means what? If two matrices of exact same order are equal to each other, that just means that corresponding entries are exactly same. So 1 1th entry here will be equal to 1 1th entry here. 1 2th entry here will be equal to 1 2th entry here. 2 1th entry here will be equal to 2 1th entry here. And 2 2th entry here will be equal to 2 2th entry here. So I am going to have 25A square plus B square is equal to 10A plus 3B. Then you will have 15A minus 2B is equal to 0. From here also you will have the same thing, and from here you will have 10A plus 3B is equal to 13. Now obviously out of these three you will be using these two to compute the value of A and B. Let's see what do we get. Here I multiply throughout by 3. So you get 45A minus 6B equals 0. Here multiply throughout by 2. So you get 20A plus 6B equals 26. Now you get what? This cancels out. This gives you 65A equals 26. A is equal to 26 upon 65. 13 into 2 is 26 and 13 into 5 is 65. So you get 2 by 5. Okay? A comes out to be 2 by 5. If A is this, what is B? B is what? It is nothing but 2B is equals to 15A. So 15A by 2 is B. B is 15A by 2. That is 15 into 2 by 5 into 2. This cancels out. You are getting B as 3. So A is 2 by 5, B is 3. Please watch out for what question is asking you. Question is asking you to compute 5A plus B. It is not solely asking you the value of A or B, or A plus B or A minus B. There is an expression it is giving you and it is asking you the value of that, 5A plus B. What will be 5A plus B? 5A plus B will be equal to 5 into A is 2 by 5 plus B is 3. So you get 5 as the answer. Your answer is 5a plus b is equal to 5. Is it clear? That's how you